guys. Good evening. I hope you're ready to learn a little combination of math and history. And the history is ancient Egypt, because I'm just slowly, getting immersed in it. I guess the more I do little episodes on it, the more I want to know. I've always, like most people, I think, been fascinated by the mystery of Egypt, because it's so old, and let me move this. Yet it was so sophisticated in its architecture, religion, general societal structure, and not to mention its math. So I don't have any real equations right now, but I was just working on some physics. I'm going to be trying to tutor for some income in the near future, and I thought I'd research and see just how the ancient Egyptians went about doing math, because to build something that is comparable in weight and size and volume to some of the most complex modern engineering feats, and have it last 3,000-4,000 years, survive earthquakes, possible floods, and entire shifts in climate, certainly must take some relatively sophisticated mathematics. So I'd like to share with you guys a little bit of what it was that I found, how these ancient people, but certainly not unsophisticated, were in fact able to develop very highly advanced and unique relative to how we do math today. And just because this is an episode about math, I might have to give the Casio a cameo. Cameo for the Casio. Cameo for those beautiful tactile buttons. Might have to take it out of the case to get it to reveal its true glory. Okay. So in this very impromptu intro, I'm going to be reorienting the camera so you guys can see what I'm drawing as we elaborate and explore the evolution and try to do a amateur fade in from my calculator sounds into the intro and the meat of this mathematical video. I'll see you guys on the other side. Bye. So the early Egyptians, they settled along, as we know by now, the fertile Nile Valley as early as about 6000 BC. So they began to record. They began to record the patterns of lunar phases and the seasons for both the agricultural and religious reasons. Because, of course, as the Nile flooded, so did their land. And like any highly developed society, especially back then, if you were depending on a crop yield and a unexpected, unforeseen, unpredictable flood ruined all of your year's harvest, all of your work, you may be hard-pressed to survive that catastrophe. So, of course, acknowledging the lunar phases. Oh boy, what am I drawing there? And the ability to use these recurring patterns, such as the lunar phases and seasonal changes, to predict when the Nile might flood, as well as perhaps how high the water table tended to rise. Of course, this was all extremely, pretty much crucial for the Egyptians to develop as a civilization and survive. So, the pharaohs, surveyors used measurements based on our body parts originally. A palm was the width of the hand. A cubit, the measurement from elbow to fingertip. And to measure land and buildings very early in Egyptian history. So we had I guess that's 4 right there. limestone maybe, that descended into the Nile, that had different markings saying low tide, rising tide, and extremely catastrophic high tides, which would be run. So, believe it or not, the fact that we have 10 digits is pretty crucial for the fact that the evolution of our counting, our number system. And the early Egyptians devised a decimal numeric system that was developed based on our fingers and our biology and our toes, you know. The oldest mathematical text from ancient Egypt discovered so far, though, is the Moscow Papyrus. Which dates from the Egyptian Middle Kingdom, around 2000 to 1800 BC. Which is 3,000 years ago. So it's thought that the Egyptians introduced the earliest fully developed base 10 numeration system. At least maybe another 700-800 years prior to this Moscow Papyrus. But even so, we think that they invented it much earlier, because the pyramids were thought to have started to begin being built maybe 1,000 years prior to that. So it just goes on and on. We don't really know when humans started being able to conceptualize numbers, let alone talk about them. So written numbers used a stroke for units. So here I'm going to try to write this down. So we have our value here. We have, a modern day of writing that is 1, 10, 100, 1,000. In America we use a comma. I know elsewhere you guys use a decimal point or a period. I'm not sure actually what you call that, because the phrase decimal point denotes that it's a fractional value. I'd be curious to know. And then we got 100,000. And then 1 million over here. So our modern value, our modern decimal-based numeric system, at least mine over here, I know in most parts of the world, I guess, numbers really aren't. They're pretty cross-cultural, aren't they? But the hieroglyph looked like, let's write that word. Uh-oh. I screwed up. The hieroglyph looked like that rather quickly when we perceive the number 10 as a heel bone, is what they called it, and a coil of rope for hundreds, which would look kind of like this. Maybe a Roman ear looks like that. And then once we get to 1,000, it becomes a lotus plant. And a lotus plant for them looked like a little triangle with some petals, a stem, and kind of a little Pac-Man feature. And I just realized how much like those little jumping, snapping, biting plants in Mario Brothers this looks like. I wonder if they were fans of, knowledgeable about ancient Egypt. So it looks like I missed 10,000. So I'll shift these two over real quick. So for 10,000, let's see, her power is up to 10 million. Let's see, it was, I don't know what that is. My little article here stops, but it looks something like maybe perhaps a reed. I don't know. A reed. A rod, maybe. And then for 100,000, it becomes something like a frog or a bird. Or a frog, which looks a lot like the same thing almost. Okay. And its little hind legs here. Wow, that just looks like my dog. Oh boy. Interesting. A little side note is that some Inuits, I believe I don't know what tribe, but I know a tribe of Native Americans worship and hold in high regard, high esteem, the frog due to its inherent wisdom and ability to diagnose the condition of the water systems, as they are both water and land animals, amphibious, I guess we'd say. And therefore, they are usually the first ones to die. Sorry for the traffic, guys. I only have narrow windows to record, so I guess we just have to deal with it. But anyways, because they are the first to be noticeably affected by polluted waters, I suppose it had a extremely evolutionary advantageous which is a huge, huge number, is, of course, as you might imagine, it's a god. It is a god. So we have a little head with a feather or a cap, and then a body with a kind of kneeling stance. Okay. But one thing to know about Egyptians was that, much like Roman numerals, they didn't have placeholders like we have here. So although it's extremely convenient for them to write large numbers that are exact like this, it's very inconvenient. So for a million, they could just draw this one symbol. But for a million minus one, I believe it took 54 characters to draw that. So for example, 4600 and 22 would look like this. I guess I'll make it a little more low resolution. So there's 4 thousands, and 600 would indeed be 6 of these. Oh, but I guess they started drawing it downwards, so maybe I should just, yeah, that looks a little better. So we do that. That's 600 and 2 tens for 22. And 2 ones. I guess they just put those right next to each other. So as you can imagine, it's a lot easier in our current form. So this famous paper that I was thinking about incorporating into this episode, but it's already a little too long and complex enough for just the time I have to put into these videos. Although I really would love to in the future, if God willing, the channel keeps growing. If I'm able to make a little more money on it, I would in fact love to get an actual, better camera, closer with 2 microphones, so you can really hear those pencil sounds that I really love. I would actually be able to just do more research and spend more time and I don't know, make more elaborate, more truly educational videos. So anyways, this rind papyrus, it's called, was, let's see, when was it created? Anyways, it was a manuscript found I think rather recently, within just the past 100 or so years. Let me see if I can find it here real quick. Yeah, Okay. It's one of the best known examples of Egyptian mathematics. It's named after Alexander Rhind, a Scottish antiquarian who purchased it. It looks a lot like this. A very beat up manuscript with holes in it everywhere. With a bunch of mathematical texts on it. And it's a very insightful look into exactly how Egyptians thought of mathematics. Because, like I said, the test of time has validated their conception as far as how proportional it is to the integrity of their monuments, their temples, their architecture, and even the less noticeable things like aqueducts and the fact that they would have had to set those pyramids extremely level, using very interesting water level tables and mathematics, of course, in combination with those. Yeah, it was purchased in 1858 in Luxor, Egypt. Found as a result of illegal excavations near the Ramesseum. So they think it dates to about 1550 BC. 1550 BC. It was in a leather roll. But that's all to say that it's a kind of instruction manual, and it was like a very popular math book, I guess. So if you wanted to get into business or trade, or you're a guy who hands stuff to other people in exchange for money, or you wanted to be a priest to help predict the cyclical celestial events that were pretty much the backbone of this entire civilization up here. This book was for you. So one of the interesting things that I'm probably gonna botch really bad, but I'm gonna try to explain because I just figured it out. And that's the true test of if you know something, I suppose, is that it explained how to multiply numbers in a way that's maybe with a Common Core curriculum, maybe that makes more sense to kids, but definitely not the way I learned to multiply. Which is you take, for instance, we have 3 times 6. What I would take is, you have a number, and you want to multiply it. Let's say we have this number, and we want to multiply it this many times. So we start off 1, 2, 3, and then we say, okay, we want to multiply that 6 times. That means we would do, right, 3 sets, or 6 sets of the original number, which was 3. So you have 1, 2, 3, 2, mislead you guys into thinking that this mathematical manuscript, being a standard for the value, being a indication of the standard of mathematical competency, was only dealing with multiplying numbers, because it certainly was way beyond that. It also did division. No, I'm just kidding. It goes way beyond that. Seriously, it contains evidence of other knowledge, such as unit fractions, composite and prime numbers, and beyond that, arithmetic, geometric, and harmonic means. Even how to solve first-order linear equations, as well as arithmetic and geometric series. And then the Berlin Papyrus, dating to a couple hundred years after that, actually showed that the ancient Egyptians could solve second-order algebraic equations, which are that just means you have an equation plus it deals with this would be a first order equation. Second order deals with squares. So when you deal with squares, generally the order of the equation just means the value of the exponents of the largest value of the exponents. So even if you have a 1 right here, the largest value would be on the x, and it's 2. If the x said 3 and the y said 2, the largest value would be 3. That would be a third order equation. So, yeah, their mathematics was definitely advanced when you consider 3,000 years ago. Most Europeans were still very nomadic and far from building monumental temples. But of course that remains to be fully determined, because we still have great monuments like Stonehenge, and of course Göbekli Tepe in Turkey that dates to like 10,000 years ago, and has huge sprawling theaters of megaliths. That's a whole nother episode though. But briefly, to explain how they go about doing mathematics. If they wanted to multiply 3 by 6, this was, and I don't think I'm going to be able to explain it right, but essentially what they did was have 2 I'm going to write it over here. Okay. So, what they did was take the number that they were multiplying it, the number that they were multiplying. So you have 3. And they would progressively double. So I guess they just started with simple concepts like doubling a number. So you have 1, 2, 3. These are just circles, not zeros. And then they would double it to get 1, 2, 3, 4, 5, 6. And then they would double that to get 1, 2, 3, 4, 5, 6, 7, 8, 9. That's funny. I drew 6 right after I said 6. 10, 11, 12. So you have 3, 6, 12, etc. And then they would just, as a reference, take the number 1, double it to get 2, double that to get 4. Let me just keep my values lined up here. And then, of course, on down. And I suppose the trick to their method here was saying which, and this was really hard for me to understand, but they simply count up which sets of the right-hand column add up to the number that they're trying to multiply this number by. So they start with their number. You just have this set aside. We're going to use this for the answer. We don't need it yet. Then they go to their reference table that they would use for any other problem and simply say, which grouping can I do this or can I do this? And obviously this would double. This would be 1, 2, 4, double to 8. 1, 2, 3, 4, 5, 6, 7, 8. And this would double to 24. Yeah, maybe I'll draw that out. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24. Because I thought it was cool when it actually clicked and worked. So we want to multiply 3 by 6. That's the ultimate goal. So we have the number 3, and we just want to group in a way that, this right column in a way that gives us the number we're trying to multiply our first number by. And the point is that this group right here is what we want, because 1 by itself isn't 6, 2 by itself isn't 6, 2 and 1 is only 3, but 2 and 4 in fact does make 6. So if we group this and we go and circle its corresponding numbers on the left, then we actually get the answer, which we know is 18, because we rigorously defined it over here. But it's weird how that actually works. So because this is the group that adds to 6, its corresponding values for the base number, the original number, add up. 12 plus 6 is 18. So that's how they did it. And just as a quick verification, as another example, what if we did, using 3, what if we did 3 times 3? And what would that be? So if we did 3 times 3, we want to group the ones column in such a way that it adds up to 3. And clearly we would use this, because plus 9. It's pretty interesting. So, for our last little bit that I teased you guys with in the beginning, we had let's see, we need to figure out how to slice bread 5 ways when we have 3 pieces of bread. Very cool. And so, yeah, this, interestingly enough, is actually the origins, the first, earliest example of a binary using the concept of binary numbers in mathematics. So, very cool. Leibniz, I think, was the first that we know of in modern times in the West, to use binary, which is simply, we have, our numbers are base 10, and that's such as, 13, or, I don't know, 21, and that means we have place values like I was talking about earlier. What place values just mean is that you start from the right and work your way left, and the rightmost value is always represents single units. And then the second one from the right in our system, our base 10 system, it's called base 10 because the second one from the right is always multiplied by 10 to get its actual value. So 3 is all the way to the right, so we take it at face value. It represents single units, so it does mean 3. But this number, 1 from the right, 1 unit left, or 1 place left from the right, represents the number multiplied by 10. So 1 multiplied by 10 is 10. That equals 13. And likewise, 1 multiplied by itself, or as a single unit, multiplied by 1 is 1. And 2 multiplied by 10 is 20. And if we have a larger number, such as 419, that just means that every shift over that we go, every place, the further you go from the right, the larger the number you multiply by. And in a base 10 system, it's called that because the number you're multiplying by increases by an order of magnitude every time, which means order of magnitude just again means order in the sense we used here, the exponent. So 10 to the power of 0, anything to the power of 0 is 1. 10 to the power of 1 is itself just 10. And 10 to the power of 2 is 100. And you can see these numbers increment. So 10 to the power of 0 times 9 is simply 9. 1 times 9. 10 to the power of 1 times 1 is simply 10 times 1, which is 10. And 10 to the power of 2 times 4, which is 100 times 4, is 400. So we get 419. except it's base 2. So this base 2 is, if you ever want to make people think that you're smart, simply write down some binary numbers and recognize that, how can I write this? This spot is base 2 to the power of 0. This spot is base 2 to the power of 1. And you can imagine just keeps going up. And this one is base 2 to the power of 3. So we just need to figure out what these actually are, and then you multiply it by that. And you got it. So 2 to the power of 0, anything to the power of 0 is always 1. So that's just 1. 2 to the power of 1 is just itself. So that's 2. 2 to the power of 2 means 2 twice, or 2 times 2 is 4. 2 to the power of 3 means 2 3 times, and that's 8. So to decipher this very enigmatic and esoteric looking binary, all we do is simply say 1 times 1 is, I'll keep it in their respective positions, so this one I'll put all the way to the right because it is at the right. You just have 1 plus 1 times 2 is 2, plus 0 times 4, which is 0, plus 1 times 8, which is 8. So that equals 11. And that's how you write 11 in binary. That's how your computer understands it, by switching something either on or off. But the Egyptians were onto that 4,000 years ago, which is so fascinating because it's what allows this to work. Okay, let me just finish here with our problem. So, practical problems of trade and the market led to the development of a notation for fractions. The papyri, which have come down to us, such as the Rhind and the Berlin and the Moscow papyri, they showed us exactly how they solved everyday, very, very practical problems. So they used unit fractions based on the symbol of the eye of Horus, where each part of the eye represents a different fraction. Each half of the previous one. So they used, just like, again, our binary chart here, where it's multiplied 1, 2, 4, 8, 16, 32. It's the opposite side of that mathematical coin. it's like, well, I guess we don't, with the internet, we don't use tables nearly as much, but anyone who's done statistics knows that tables are invaluable. Okay, so unit fractions could also be used for simple division sums. For example, if they needed, here's our famous problem now, they needed to divide 3 loaves of bread. Let's pretend that these loaves are indeed the same size. So, and this is a practical problem. Is that with a V of that good Egyptian bread? 4, 5. Nice. Egyptians. They're hungry, so it wouldn't be fair to give them less. So, we only have 3 loaves, but how do you divide this equally? So what they would first do is divide the first 2 into 3. Of course, equally. Then what they would do is take the 3rd loaf and divide it into 5ths. So that's pretty much, looks like a star. 3, 3, and 5 pieces. So, now what they would do is say, out of these, we want to take 5 of these pieces because we have 5 people. Doesn't matter how many are left over, we just know that these are all the same size. So each person would get, let's pretend that's 1/3. Yeah, that looks too much like 1/5. So each person gets 1/3 plus, so they get 1/3 plus 1/5. Make that a little bit tinier. Okay. So that would take care of each person would get, that would take care of all of these, because each person would get, there's 5 people, each person gets a slice. That means this whole piece is now equally divided, used up. And mean, like, why wouldn't they divide it all into 5 and give each person one slice? That would be 3/5. But hey, this is how the Egyptians did it. Okay, so we want to give each person that, and there's 5 people. So we multiply it by 5. So there's 1, 2, 3, 4, and 5, and we'll have this piece left over. Now what they did was divide this into 5. 1, 2, 3, 4, 5. And so all they had was this piece left right here. Which, if you did the math, would be 1/15. Each piece would be 1/15 of the loaf. So each person would get that much. Plus 1/15. Which equals 1/3 plus 1/5 plus 1/15. Which equals 3/5. Yeah, I don't know why that's easier than just dividing them all into 5. But I guess that probably makes it way more practical on other examples. This was probably just a bad example. Let's see, the Egyptians. Clearly, for the Egyptian pyramids, there were, of course, 4 sides to the pyramid. They knew that the height the actual height of the pyramid was intimately correlated, so they knew that the number of blocks they needed was proportional to the volume and the volume equals 1/3 times the height times the length times the width. So that's the height, and this would be the width. And here is the length. I guess I'll make them all capital. So times width, and then they would know exactly how much space they would need to fill it up. And this was as well as So as well as truncated pyramids. So if they needed to clip a side, clip the top off, they knew exactly how much they would need. They just do this minus this, and that gives them this whole volume of the bottom part. Sorry, there's lawnmowers in the background now, and I have no other time, so I'm just gonna wrap it up. But long before the Pythagoreans, they knew that a triangle with the sides 3, 4, and 5. Was it 5, 3, 4 yields a perfect triangle. So the Egyptian builders used ropes knotted at intervals of 3, 4, and 5 units. 4, 5. So what that would do is this one would go right there, and then this one